I want to do a set of problems in this video that will go from fairly elementary Newton's second law problems up to things that are a little bit more advanced, and we'll just kind of dive in and do these things. The first one, we have a pitcher releasing a baseball of weight 1.4 newtons with a speed of 38 meters per second by uniformly accelerating his arm for 0.092 seconds. Through what distance does the ball accelerate before it's released? And then what average force is exerted on the ball to produce this acceleration? Well, this is a Newton's second law problem. We're going to be talking about F equals ma. And something that we'll kind of have to assume here is that it's one-dimensional motion, and let's just suppose that it's horizontal, so that's what we have going on there. So if it's one-dimensional uniform acceleration, we can write equations like x equals x naught plus v naught t plus 1/2 at squared, and we can also write v equals v naught plus at. We're going to simplify this very much and just ignore gravity and act as if that pitcher pushing on the baseball is the only thing there is. And actually, it will be the net force, so it's not too much of a stretch. First thing, through what distance does the ball accelerate before it's released? Well, we know how long it's going to accelerate for. We know the final speed, 38 meters per second, and we should be able to figure out what the acceleration is based on that. And so we'll be able to work that out. In fact, the acceleration is just going to be delta v over delta t. Presumably here we're accelerating from rest, so at some instant the pitcher's arm won't be moving, and then at the end it'll be moving at the final speed of the baseball. So we'll have v minus v naught here divided by delta t, which is just going to be v over delta t. And we get that the acceleration, plugging in the numbers here, 38 meters per second divided by 0.092 seconds is going to equal 4.1 times 10 to the second meters per second squared. So actually that's 410 meters per second squared, 41 times the acceleration due to gravity. So it's pretty fair to ignore gravity in this situation. Actually, the pitcher would be having some upward force on the baseball, so it's only moving horizontally, and that'll cancel out its downward weight. But there we have the acceleration. Now, can we figure out what distance does it accelerate, through what distance does it accelerate before release? I think we should be able to do that here. We can use the x equation. We can just let x naught equal 0, measure from there. V naught we know is 0, and so x is actually just going to equal 1/2 at squared, and we just plug in the numbers on here. We know the acceleration, 1/2 times 4.1 times 10 squared meters per second squared times the time, which is 0.092 seconds, if I remember right. Yes. And that gets squared, and we find out that the position or the distance that it travels through while it's being accelerated is, that is 4.1 times 10 squared. Okay, just about 1.7 meters, which makes sense. A person is 2 meters tall. If the person has a fairly long arm and they swing it through some kind of thing, this might be about the distance. And also the pitcher's usually stepping forward as they're accelerating the baseball. So we have that. The second part asks what average force is exerted on the ball to produce this acceleration. Okay, it's the force that's doing the accelerating, but the thing that will let us figure out what this is to do F equals ma. Whoops, forgot the equal sign there. We know the acceleration, we don't know the mass yet. Okay, we're given the weight of the baseball, but the weight of the baseball is equal to its mass times the acceleration due to gravity. So the mass will equal the weight divided by g. Weight is 1.4 newtons. You may be unfamiliar with the unit of newtons, but if I just divide it by that, let's see, 1.4 newtons divided by 9.81 meters per second squared, we get 1.4 newtons. Remember, a newton is a kilogram meter per second squared, and I don't usually bother to write that out because I have it memorized. It's just stuck in my head. And just divide 1.4 by 9.81 and we get a mass of 0.14 kilograms. And then the last thing is just do F equals ma. F is equal to that 0.14 kilograms times the 4.1 times 10 squared meters per second squared. And we get a force of about 58 newtons. So kilogram meters per second squared, that combination of units is what we call a newton. And so we have that. So there was a fairly elementary problem. It was kind of a combination of our one-dimensional constant acceleration motion with introducing a first Newton's second law calculation. Let's take a look at this one. If a man weighs 912 newtons on Earth, what would he weigh on Jupiter, where the acceleration due to gravity is 25.9 meters per second squared? Okay. Well, weighs 912 newtons. That means the weight is equal to 912 newtons. Weight is mg. So we can figure out what the mass of this guy is and then take him to Jupiter. Okay, this is g on the Earth, the little g on the Earth. By the way, when we study gravity next quarter, we'll find out that the acceleration due to gravity, if you know the mass of the planet and its radius, you can calculate what the acceleration due to gravity is at that point. Now, to be on Jupiter, it's a little bit weird because Jupiter doesn't have a surface like Earth does, and you could descend into the clouds on Jupiter and you'd keep going for a long ways, and eventually you'd reach a point where you're going through a state of matter called liquid metallic hydrogen, and eventually there may be some kind of a solid surface, but you'd be a long ways down before that happens. And so we'll just pretend that there's a helium balloon floating at the top of Jupiter's cloud tops, and you could stand in the basket of that and it would be as if you were standing on a surface at that point. Anyway, we need to figure out what the mass of this person is. The mass is just going to be 912 newtons divided by 9.81 meters per second squared, which comes out to be about 93.0 kilograms. And on the surface of the Earth, that person would weigh about 205 pounds. So not quite as unusual as it sounds when you express it in newtons, in 912 newtons. So what about on Jupiter? Well, the weight on Jupiter will equal that mass That mass is due to the number of protons, neutrons, and electrons in that person and the way that they combine together to form atoms and nuclei. And that's not going to change when you go to Jupiter. They'll still combine together the same way. So we'd have the mass times the acceleration due to gravity on Jupiter, 93.0 kilograms times our 25.9 meters per second squared. And on Jupiter I get about 2.41 times 10 to the third newtons. So 2,410 newtons about, more than 2.5 times as much as they would weigh on Earth. So you'd be kind of tired moving around there. If you wanted to know the weight on the moon, so W sub moon, Earth's moon that is, you'd just take that mass, 93.0 kilograms, and I think that's a kilogram. A little sloppy. Anyway, 93.0 kilograms times, we've done a problem with this before, 1.61 meters per second squared. You can see the acceleration due to gravity on the moon is a lot less than it is on Jupiter. It's also only about 1/6 what it is on the Earth. And so you could figure those things out all you wanted. You'd actually end up with about the weight on the moon equaling just about 1.50 times 10 squared newtons. So that's only about 1/6 of what it is on the surface of the Earth. And if you watch the old Apollo moon landing videos and watch how the astronauts moved around on the surface, they were kind of hopping around. They were having a good time. It was sort of fun for them to move around there. Okay, there's a relatively simple weight problem. Here's another one that will be a little bit unusual, but a heavy freight train has a mass of 15 tons, and that's the spelling for a metric ton. If it was just American unit tons, it'd be TONS. So what in the world is a metric ton? Well, 1 metric ton, which is 1 TONNE, is equal to exactly 1,000 kilograms. So the mass of this train is going to be, if I write that in scientific notation, 1.5 times 10 to the 1/234 tons, or I don't know if, well, it's got an S at the end, must use that for that, times 10 to the third kilograms per ton. You get that it'll be 1.5 times 10 to the 7th kilograms. So that's quite a bit of mass for that train. That's 10 to the 7th is 10 million, so about 15 million kilograms. Anyway, that's a lot. If the locomotives can exert a pull of 750,000 newtons, how long does it take to increase the speed from 0 to 80 kilometers per hour? We're going to have to do some unit conversion here, but let's figure out the acceleration of the train first. And when I do Newton's second law problems, I've got this list of things that I usually do. This one's simple enough you could get away without it. But if I was to draw a picture, I'd make a really simple picture here. This is going to represent the train, just one little car with that much mass. And so there's my sketch, and then I've got this engine pulling on it. It's got bigger wheels, and I can't draw the modern streamlined ones very well, so we'll imagine that this thing looks more like a tractor. Anyway, if it's a steam engine, it's got this smokestack up front and stuff like that. So there we go. And this thing is what's exerting the force on this massive train here. So there's a sketch. If I then do a free body diagram for that thing, here's what I'll have. I will have its weight downward, a normal force acting upward, and I use a lowercase n for my normal forces because I don't want to get mixed up with normal force and the units for force. And then we have a horizontal force that is the pull of the engine, and I'll call that F sub E. That's the force of the engine acting on the train there. Then, now I'm turning this into a two-dimensional problem, which isn't necessary because we know all the actions taking place in the horizontal direction. But if I was to do that, the next thing I would do would be to write Newton's second law in vector form, which in this case would be F sub E plus N plus mg equals ma, mass times acceleration. Draw a coordinate system, so I'll let x point to the right and y point up, and then write each vector that I've got here in terms of that coordinate system with I hat and j hat components. This is actually pretty simple when your forces are all either pointing toward the y or the negative y or the x or the negative x direction. So I'll just list them here. The force of the engine, the vector, is going to be the force of the engine in the I hat direction. Okay, it's pointing that way. The normal force is just its magnitude, whatever that happens to be, in the j hat direction. It's pointing in the positive y direction. mg, as a vector, is pointing in the negative y direction. That makes it minus mg along j hat. And what else? Oh, the acceleration. Well, it's going to be to the right. So ma is going to equal whatever the acceleration is in the I hat direction. Now, what I do when I've got a two-dimensional problem is I'll just look at some of the components. So I'll look at the sum of the forces in the y direction is going to equal ma in the y direction. What have I got in the y direction? I've got an n and a minus mg, so that those forces, when I write a scalar equation, become n minus mg. And there's no acceleration in the y direction because you won't see this train jumping off the track, and you don't see it falling into the earth either, so that's just going to equal 0. And all that tells me is that the normal force is equal to the magnitude of the weight. Okay, that's going to happen in a lot of problems. Now, what about in the x direction? Some of the forces in the x direction, well, all I have is the force of the engine, and that'll equal ma sub x. So I'll have the force of the engine will equal ma sub x. Okay, well, that's the only acceleration there is. The acceleration in the x direction will equal the force of the engine divided by the mass of that thing. And I'm going to write that force of the engine in scientific notation. So 7.5 times 10 to the 5th newtons divided by the mass of the train, which is 1.5 times 10 to the 7th kilograms. Now remember, a newton is a kilogram meter per second squared. The kilograms divide out, and I'll have meters per second squared when I'm done over here. And I can do this one in my head. 7.5 divided by 1.5 is 5.0, I believe. Check that to make sure. But 5.0 times 10 to the 5th divided by 10 to the 7th is 10 to the minus 2. So 5.0 times 10 to the minus 2 meters per second squared. That's actually 5.0 centimeters per second squared. So it's not a very large acceleration, and if you ever watch a train start up from rest, you wouldn't be surprised to see a number that small for the thing. So how long will it take to get from 0 to 80 kilometers per hour? Well, it's undergoing constant acceleration. When that's the case, we know that v will equal v naught plus at. Let's see, increase the speed from 0. That sounds like v naught is 0 to me, so v is just going to equal at. And the only problem is that speed is in kilometers per hour. So, but we can fix that. We have 80 times 10 to the third meters per second times, oh, I did something. I used the k from kilometers and just changed it into 10 to the third. Anyway, times, nope, that's meters per hour, excuse me. And so I'd have 1 hour on top and 3,600 seconds on the bottom, meters per hour. There we go. Anyway, that comes out to about 22 meters per second for 80 kilometers per hour. And v equals at. The time it'll take to do that will be v divided by a. For some reason, oh, I know. I've only got one significant figure on that number, so I just have to write it as 20 meters per second. I was looking at my notes and wondering why I'd done that. So the time will equal that velocity divided by the acceleration. So I'll have 20 meters per second divided by 5.0 times 10 to the minus 2 meters per second squared. And meters per second divided by meters per second squared, invert and multiply, and you'll end up with seconds. Convince yourself of that. I'm seeing a lot of calculations with no units in them and then units magically appearing at the end. That is magic. Okay, that doesn't follow the rules of algebra, and so don't do that. 20 divided by 5 is 4. I'll have 400 seconds is what I'll get. 4 times 10 to the squared seconds. Okay, that's about 6 minutes. Maybe that's a bit quick for a train to accelerate from 0 to full speed. I don't know, but it seems like when I'm waiting for the trains to cross in Cheney, they're not accelerating very fast. Okay, there's another problem. Now, we didn't have to go through all that vector stuff, but I did it because we'll have a lot of problems where we will have to do that. In this problem, I could have just said F equals ma. We have the force, or we have the mass of the thing. We know the force. We can figure out the acceleration both in the same direction. So I went to a little more trouble than I needed to on that one. Okay, this one's a bit more complicated. We have a 5 kilogram mass placed on a frictionless horizontal table and connected to a cord that passes over a pulley and then is fastened to a hanging 10 kilogram mass. Find the acceleration of the two objects and the tension in the string. Now, on the list of things I have you do when you're solving a Newton's second law problem, the first thing on the list is to make a sketch. And so I'll do that here, and just kind of a partial sketch. There's the tabletop. Here's a table leg, and the floor is down here. So, and here's the way I draw a pulley. Just stick something on there like that, and then there's going to be this mass sitting on the tabletop, and it says 5 kilograms. I'll denote that as m sub 5. Okay, and then there's something attached to that, a string of some sort, a cord they say, that passes over that thing and is fastened to a hanging 10 kilogram mass. So this will be m sub 10. And this is kind of a screwball problem. We've got 3 sig figs on this and only 1 on this that we know for sure. So when I typed this up, I should have been paying attention and introduced a third significant figure on that. But I don't really care what the number comes out to. I want to show you how to solve this, and we'll work that out. So there's our sketch. Now, the next step in a Newton's law problem, Newton's second law problem, is to make free body diagrams for both of these objects. They're 2 separate objects. And so I'll start just by drawing those things. So here's what I have here. For the 5 kilogram mass, and I'm denoting its mass as m sub 5, one of the forces on it will be m sub 5 times g, and that's a vector now. G as a vector points down. Its magnitude is 9.81 meters per second squared, but that's how that works. And then there'll be a normal force provided by the table on that thing, and then it's being pulled to the right by a tension that's acting on it. And I'm going to label that as T sub 5. That's the tension acting on the 5 kilogram mass, and that's how I denote it. Okay, what about the 10 kilogram mass? Well, we only have 2 forces acting on it. We'll have the mass of the 10 kilogram mass times g, and it's tied to a cord, no normal force acting on it because it's not sitting on a surface, and I'll call that T sub 10. That is the tension that's pulling up on that 10 kilogram mass and keeping it from falling downward as fast as it might otherwise do that. By the way, there's kind of a joke in some classes when you get done with taking engineering statics, you know, 2 things, F equals ma, and you can't push a rope. You can't push a rope. The rope pulls on you or pulls on that, but it can't push objects. So keep that in mind. Anyway, there's what we've got. Now, once you have a free body diagram, the next thing to do is to write Newton's second law in vector form for this object and for that object. And I'm going to have to be working separately here because I've got these 2 different objects. So for the 5 kilogram object, here's what I'll have. I'll have n plus m5g plus t5, and these are all vectors, is equal to ma. Whoops, that's m sub 5 times a sub 5. Got to be careful here because these 2 things have accelerations in 2 different directions, so they can't be the same acceleration. And I have to be careful to use the appropriate mass on this equation. And by the way, all I was doing here is just writing the sum of the forces equals ma. And then, well, I'll go ahead and write the Newton's second law for that 10 kilogram hanging mass. I would have, oh, which way do I, well, in terms of Newton's second law, whoops, I'd have, in vector form, I'd have T10 plus m sub 10g. Okay, that's the sum of the forces. They're being added together as vectors, and that will equal the mass of the 10 kilogram object times its acceleration. Okay, so far I haven't picked coordinate systems or anything else for these 2 objects. All I've done is just draw that. Now the next thing to do is select a coordinate system, And I'm going to use different coordinate systems for the two things, although, well, I'll show you what happens if I use the one. But I'm just going to let x point to the right and y point upward. And then I can write all of these forces in terms of that coordinate system. And it won't be hard, because if I look at those, they either point up, down, or sideways. And so n is just going to be its magnitude in the j hat direction, because it points up, and so does y. M5g, let's see, M5g is pointing downward. It's just going to be minus M5g in the j hat direction. I'm going to kind of try to stay parallel here. T5, oh well, I'll go ahead and add more paper if I need to. T5 is pointing to the right. That's the positive x direction. So it's just going to be whatever its magnitude is in the I hat direction. And then M5A5 will equal, it's going to be to the right also. This thing is going to pull that mass to the right, or the tension will. So we'll have whatever its magnitude is in the I hat direction. Okay. All right. Well, I usually do this. I go sum of the forces in the y direction. Sometimes we care about these. This time we don't. Will equal the mass. Well, actually it equals 0 in this case, because there's no acceleration in the y direction, because it's sitting on this thing and it's being pulled straight to the right. So those will end up equaling 0. And if I look at those forces, this will tell me n minus m5g is equal to 0. That just tells me the normal force is equal in magnitude to the weight of the thing. Right. Now, we don't need that here, but soon we're going to be studying frictional forces, and it turns out the frictional force will be proportional to this normal force. And so then we'll need to worry about that. But here we don't. In the x direction, the sum of the forces in the x direction will equal m5a5. Well, what have I got? I only have the T5 acting in that direction, and so the tension acting on that 5 kilogram mass is what's producing the acceleration. So M5A5. Okay. Something happens if I choose this same coordinate system for the hanging mass. And I'll just show you what happens. For the hanging mass, if I write its forces in I hat j hat form, I'll get T10 is acting upward on it. So as a vector, T10 will just equal its magnitude in the j hat direction. M10g will equal the negative of its magnitude in the j hat direction, because it's pulling down. And then M10A10. This is a vector. What direction is it going to accelerate? Well, it's going to accelerate down. Okay. It's going to be the thing that's dragging that 5 kilogram mass across the tabletop. And so this will equal minus M10A10 in the j hat direction. So for this thing, what I'll get is, let's see, some of the forces in the y direction, there aren't any in the x direction, will equal M10A10. And what I end up with is T10 minus m10 times g is going to equal minus, actually, let's go ahead and write it as m10a10. Okay, and just leave it at that for now. So I'll kind of ignore that. Pretend I don't know what direction the acceleration is going to be, but I'm soon going to have to figure out how to deal with that. So let me slide this over here a little bit. We won't be able to see everything, but actually as long as the T5 equals M5A5, we know that. So here's what we've got so far for equations. We have T5 equals M5A5, and I have T10 minus M10G is equal to the mass of that 10 kilogram times the acceleration of that 10 kilogram. Okay, so those are two separate equations there. But I can do something. For instance, when you have a pulley, the whole point of a pulley is to let tension in the string pass over it with as little loss as possible. And in this class, whenever we have pulleys, we just pretend they're frictionless pulleys. We'll actually do a lab where we use pulleys, and the ones that we use have so little friction, you can give one of those things a flip with your finger and it'll just keep spinning for a long time. So very little friction. And when that's the case, the tension on one side of the pulley will equal the tension on the other side. So I can say that T5 is equal to T10, and I'm just going to let T stand for that. So that simplifies things a bit. Now I've gone from three unknowns, T5, A5, or four unknowns, T5, A5, T10, A10, to three unknowns, but I can go farther than that. These two masses are tied together by a cord, and whatever distance M10 travels through downward, M5 is going to travel that same distance sideways, and the accelerations and velocities will end up being the same as well, except with y being positive upward and x being positive to the right, which you can't see. Here's the coordinate system I chose. I'll move that back out of the way. But if mass 5 is moving to the right, it's going to have a positive acceleration. But with mass 10 moving downward, it's got a negative acceleration. And so the signs of the two accelerations are opposite, and A5 will equal the negative of A10, or vice versa. But let's just let A5 equal A, and that tells me A10 will be negative A. Okay, now with that, here's what the equations become. I get T is equal to M5A, and I get T minus M10G will equal, A10 is the negative of A, it will equal minus M10 times A. Okay, that's a little bit weird, but let's see what we can do with it. I can take this thing, which is this is equal to T, and I can substitute that in there, and I will get M5A minus M10G will equal M10, minus M10A. Almost lost that minus sign. Now, if I kick this across, it'll change sign. If I bring this across, it'll change sign. And I'll have M5A plus M10A will equal M10G. And over here, I've got a common factor of A. I can factor that out. a times m5 plus m10, m10 is equal to m10 times g, or the acceleration will equal m10 times g divided by m5 plus m10. This is Newton's second law. Okay, m10g, that's the weight of this hanging mass. It's the thing that does the work on both of them. But the weight of this thing doesn't just accelerate the 10 kilogram mass, it also has to accelerate the 5 kilogram mass there. And this is like F net divided by, I'll write it as a capital M. It's the sum of those two masses. It's the total mass that has to be accelerated. And so this kind of makes sense that that's the result that we have. Now, we could plug in the numbers here, but this is where we'd have to start sweating about the difference in sig figs between the 5 and the 10. If we just kept them, I don't know. Getting to here is the interesting part of the problem for me. Plugging in the numbers is not so interesting. But that's how you do a two-body problem. You can get Newton's second law in scalar form, which is what we have up here. We have two equations for those two things, and then you have to do a little bit more work. When it's pulleys, you have to recognize the tension's going to be the same on both sides of the pulley, so you don't have to identify it separately, but it's good to work this far before you try to equate those things. And then with the acceleration, you have to be a bit careful. Now, something that I like to do is that I look at the problem ahead of time and I think, okay, if the mass that's on the plane is going in the positive direction, then the mass hanging is going to be going down. I'm going to use a coordinate system for that downward one that makes down the positive direction. And so what I do is, for the mass on the plane, I just go ahead and use my regular XY thing. But for the hanging mass, I do a coordinate system that looks like this. We don't even need an X for that one, but we can let Y be positive downward. And then they'll both have the same sign to their acceleration, and I can deal with it that way. So in this case, the Newton's second law for this hanging mass would then become m10 times g minus the tension ends up equaling m10a10. And for the other one, we would have t equals m5a, and just kind of keep going with that stuff. Plug this in. I'd have m10g minus m5a is going to equal m10. Actually, by this time I recognize that a10 is equal to a5, so I just have an a there. And a little bit of algebra and I'd end up with the same thing here that I had on the other one. But sometime I'll have another problem and I'll sort of pick that to be the case, and we'll see what happens. Okay, there are more problems, I think. Yeah, this one ends up being very similar, or the last two are tied together here. Something interesting about this problem: we have a block released at the top of a frictionless incline. You'll see a fair number of frictionless situations until next week when we start considering friction. But the incline is 5.00 meters long and makes an angle of 22.4 degrees with the horizontal. So this is something that we have to make a sketch for this thing. So let's do that. And I exaggerate the angles when I'm making sketches. I don't try to make this thing 22.4 degrees at all. But let's just pretend this is theta and it's 22.4 degrees. And we have a block sitting up there on there. I'll just give it an M there for its mass, and it's 5.00 meters from the bottom of the plane. And the question is, what's the speed of the block at the bottom of the plane? Okay, well, I've got a sketch. The next thing is to make a free body diagram, and this one's going to be a little bit more complicated, but here's the low-hanging fruit. Okay, drawing MG. We'll be doing that on almost every free body diagram we have, and so that's the easy thing to do. And then for getting the other thing that's acting here, I need to sketch in a 22.4 degree angle on here. The normal force is always perpendicular to the surface. In fact, the word normal in mathematics means perpendicular to. And so that's what we mean by a normal force. And so I'll try to draw something here that's perpendicular to that angle that I've got there, and that's the normal force. Okay, and that's it for my free body diagram here. There isn't much more. Turns out it's the component of mg that's down the plane that will produce the acceleration. But Newton's second law in vector form here is going to be n plus mg is going to equal ma. So that's Newton's second law. The sum of the forces is equal to ma, and it's a vector sum here, so we'll have to figure out some things. Okay, now what about a coordinate system? Well, I'm going to do something weird with that. I'm going to let x point down the plane, that's x, and y be perpendicular to the plane. Okay, they're still perpendicular to each other, so it's just an xy coordinate system. It'll make it easy to calculate the normal force, but I'll have to do some work to figure out what mg is, and I'll show you something that I have to do to figure that out. So now I write each of the vectors in component form. I'll do n. That's pointing in the positive y direction, so it's just going to be its magnitude in the j hat direction. ma, well, I said x points down the plane, and that's the direction it's going to accelerate, and it's not going to jump off the plane, and it's not going to sink into the plane, so ma is just in the positive x direction. So ma in the I hat direction. It's mg that I have to do a little bit of work for. And let me show you something. I drew the normal force perpendicular to the plane. Now, this is theta here. This angle here is going to be 90 minus theta. If you do that math in your head, you'd get something like 67.6 degrees or something like that. But I'm just going to call it 90 minus theta. And then down here, this is a right angle here. So this angle will be 90 minus this angle. 90 minus theta. Well, that's theta. So this angle ends up being theta. Okay. That means I can draw myself a little right triangle that has mg as the hypotenuse, and it'll have a component of mg that is into the plane and a component that is down the plane, and this angle is theta. Well, this side divided by this hypotenuse will equal the sine of theta. And so work through this in your head and make sure you understand this. This will be mg sine theta. This side divided by the hypotenuse is going to be the cosine of theta. So this side will be mg cosine of theta. So make sure you can figure that out. All right. Sometimes we've done things where we have something times the cosine of theta is equal to the x component. Well, that's not the way it is this time, because our angle of theta is actually measured off of the negative y-axis. And so we get something weird. Anyway, we'll have mg is going to equal mg sine theta in the I-hat direction minus mg cos theta in the j-hat direction. Okay. What have we got? Oh, let's look at the forces in the y direction. Okay. Sum of the forces in the y direction is going to equal 0. That's not the direction of the acceleration. So all I'll have is n minus mg cosine theta. Equals 0. Well, that tells me in this situation the normal force isn't equal to mg. It's mg cosine of theta that normal force will equal. So when we do friction problems with something on an inclined plane, we're going to have to work a little bit harder to figure out the normal force. Okay. Sum of the forces in the x direction is going to equal ma. Well, what have we got for forces in the x direction? The only thing we have is mg sine theta. Now, I forgot to bring this up before, but they never told us what the mass of the block was here. Turns out it doesn't matter, because when we're figuring out the acceleration, the masses divide out, and we just get that g sine theta is equal to the acceleration. Now, let's see if that expression makes sense. Okay. We'll look at a couple of extreme conditions. What if theta is 0? That makes this plane being a flat line. In that case, there's no acceleration because the sine of theta is 0. And so we'd have the acceleration is 0. Well, that makes perfect sense. What if theta is 90 degrees? What's the sine of 90 degrees? It's 1. That means instead of having an inclined plane, you've got a wall. And if you set something on a wall and let go, it's just going to accelerate downward with an acceleration of g. And the sine of theta being, sine of 90 degrees being 1 shows that. So this expression that we got for the acceleration makes perfect sense here. What else can we do with this one? Well, now that we know the acceleration, it's released at the top of a frictionless incline, 5 meters long. What's the speed of the block at the bottom of the incline? Okay, well, I don't want to have to mess around with time and figure stuff out, but I've got an equation that lets me get away with that. I'll have v squared minus v naught squared equals 2a delta x. Remember, x is down the plane here. V naught is 0 because it's starting from rest. It's released at the top of the plane. So this thing is 0. And I know that the acceleration is g sine theta. So I'll have v squared is going to equal 2 times g sine theta times delta x. That's the 5 degrees. And you can plug in the numbers here. You'll have 2 times 9.81 meters per second squared times the sine of, now we finally put the angle in, 22.4 degrees times 5.00 meters. Okay, and we've got everything we need there. And I think when I did this, I came up with 6.11 meters per second. You can check that to make sure. But that was kind of a fun problem. Now let me show you another way to get that. And this is something that every once in a while will have a problem that comes out this way. When I wrote the vector expression, I had n plus mg is equal to ma. This is an example of what we call a three-vector problem. And you can solve this graphically, almost completely graphically. So let me just draw the situation here. And draw, this is the inclined plane. I know that the normal force is perpendicular to that. So here's the normal force. And again, normal force is perpendicular to the inclined plane. Okay, I add to that mg, excuse me, and mg is downward. Okay, well, what about lengthwise? It's going to point down along this line, but n plus mg equals ma. When you draw ma, you're going to draw it from the start of n, or the tail of n, to the head of a. But what direction does ma point? It points straight down the plane. And so this is ma, which means that this diagram has to be the correct orientation here. Here's mg. And this is a perpendicular angle here. Well, you could reproduce this thing and just say, I've got a triangle, this is n, side n, this is perpendicular, this is ma, and this is side mg, and what's that angle up here? Well, let's see, how did I figure out a way to show that to you? I did figure out a way, but I can't remember what it was. Turns out it's 22.4 degrees again. Here's how I did it. I just take a parallel line up here. This is theta down here. This is theta here. This is 90 minus theta. This angle is 90 minus 90 minus theta. It's theta again. So here's theta. Okay, well, ma over mg in that triangle, that's the opposite over the hypotenuse. That's the sine of theta. The m's divide out, and a equals g sine theta. So when you have a three-vector problem, you can do that. You can go ahead and do something like that. Now, most of the time when we have three-vector problems, there'll be things where two of the vectors are perpendicular to each other, and that's what makes this one particularly easy to do. If they're not perpendicular, but you still know some angles, you could use the law of cosines or the law of sines to do a little bit of work. I had a student the very second year I was at Big Bend, so he would have been starting in fall of '94, and he could solve more problems with the law of sines than anybody I ever saw. And it was kind of neat. He ended up going on and getting I think a master's in mathematics, mathematics and actuarial science, and then going on and getting a PhD in economics, and having an interesting life anyway. So I'm going to stop there. There's one more problem somewhere in that set, but see if you can solve that one on your own. It's the same incline as the previous question, but this time the block is given a shove up the incline with an initial speed of that much. How far up the incline will it go before stopping? So see if you can model these same sorts of solutions and figure that one out.